Great. So we are very happy to have Reece with us today from Harvard, and he's going to tell us about Chern-Weil symmetries and how gravity avoids them. So go ahead.
Okay, thanks. Yeah, so this is work that I'm doing with several collaborators. Ben Heidenreich, who's a professor at UMass Amherst, Tom Rodelius, who's now a postdoc at Berkeley, Miguel Montero and Irene Valenzuela, who are postdocs at Harvard, and Jake McNamara, who's a student at Harvard. And what we're interested in is this idea of sort of one of the oldest swampland conjectures that long predates the name swampland, which is that theories of gravity should not have global symmetries. And so we're interested in exploring the implications of this idea, and what we've noticed is that there's this set of symmetries that have kind of been right under our noses all along, but that people don't often talk about as symmetries. And it's interesting to think about them and think about their implications. And before I get into that, I'm going to start by just kind of reviewing the idea of a generalized global symmetry, which some of you may be familiar with, but some of you may not, and how it relates to some of these swampland ideas like the weak gravity conjecture. And then in the second half, I'll talk about what we're calling Chern-Weil global symmetries and how they might have interesting phenomenological applications. So before I tell you what a generalized global symmetry is, let me just briefly review kind of how to talk about symmetries in the language of differential forms, because I'm going to be doing this throughout the talk, and it may not be the most familiar way of doing this for some of us, especially those of us coming from a more phenomenological background. We're used to saying that a conserved current is something that has a vector index and the divergence of that vector is 0. But we can always dualize that. So in 4 dimensions, we would turn this thing with 1 index into something with 3 indices by taking the Hodge star, which is effectively just contracting with some antisymmetric symbol. And the statement that the divergence of the current is 0 translates into the statement that this other current, this 3-form current, is closed. So the exterior derivative acting on it gives us 0. And this language is kind of nice because ordinarily you might have said that to find a charge, you take some spatial slice and you integrate the 0 component of the current. In this language, this just becomes saying that you have some d-1 dimensional slice of spacetime and you just integrate the form over that. And in this language also, gauging is very simple. We're just taking this wedge product of our current with the gauge field. And the equation of motion in Maxwell theory has a nice form that d of star f is this 3-form current j. And that means that when you gauge the current, it now becomes not just closed, but exact. So J is now D of something else. And so you can think of gauging as removing these currents from the cohomology. And I've been sloppy on the left-hand side of these equations about square root of G's, but the right-hand sides are all correct, exact formulas. Okay, so this is a nice language for thinking about symmetries. And for an ordinary symmetry, one thing you can do with this is construct charges, as I said, by integrating this current over a manifold. And for an ordinary U1 symmetry, you'll get some integer when you do that, but in the quantum theory, you have operators associated with these charges. And so there's a family of operators for elements, for phases alpha, so e to the I alpha is an element of U1. For every such element, you can construct an operator associated to a given submanifold of spacetime by integrating the current and exponentiating I alpha times that integral. And these operators are topological, which means if I take this manifold over which I integrate the current and I squish it and stretch it, as long as I don't cross the boundary of that manifold through something that's charged, I don't change any correlation functions. Okay, so if I have some charged operator V, and I have this symmetry operator U that's associated with my global symmetry group, if I move my charged operator through this manifold, I pick up a phase that depends on the charge Q that the operator has. And one reason why this way of formulating symmetries in this language of having symmetry operators associated with submanifolds of spacetime is a useful thing to do is it works very nicely for discrete symmetry. So for a discrete symmetry, you might say there's sort of no local notion, it's a global thing. But in fact, even for a discrete symmetry, we can define these operators associated to submanifolds, and they can act on operators in this way, even though there's not a local conserved current that we integrate to get these operators. And so this way of thinking about symmetries, it's been lurking in the background of things many people have been doing for a long time, but it was kind of codified in a paper by Gayotto, Kapust, and Seiberg and Willett in 2014. And they generalized this to the notion of P-form symmetries. And The general idea is the same. So we now have operators that are associated with q-dimensional submanifolds. Okay, so instead of just having point-like local operators that are charged, we might have some operator associated with a line. But the idea is that we can always surround this q-dimensional thing with something of d minus q minus 1 dimensions so that they're topologically linked with each other. Okay, so like in three-dimensional spacetime, I could have two different circles, one-dimensional manifolds that are linked with each other topologically. And a symmetry is associated with these topological operators such that when I shrink them to surround the charged object, I just multiply that charged operator by some sort of representation of the symmetry. So in the U1 case, this was just the phase, e to the IQ alpha. More generally, this could be some matrix that represents the gauge group. But this is the idea of generalized global symmetries. As I said, it came from this paper by Gayotto and collaborators. And so the general case is a p-form symmetry. The charge operators or the symmetry operators that implement these symmetries are these topological operators that are associated with d minus p minus 1 manifolds. And the charged operators for p-form symmetry are p-dimensional. So the ordinary case is zero-dimensional, and our charged objects our charged operators are just local things. For example, in the one-dimensional case, the charged objects are line operators like Wilson lines or Hooft lines, and this generalizes. And these charged operators can also create charged objects, which have one extra dimension, just like a charged local operator can create a point particle that has a one-dimensional world line that extends through time. Wilson line operator can create some string-like charged object, and so on. And in the case that G is continuous, you can think of these symmetry operators as coming from integrating some local current, which is closed, as I was mentioning before. But more generally, you could define discrete groups in this way. And the group structure is related to a product law for these operators. If I take two different operators on the same manifold associated with different group elements and multiply the operators, I get the operator associated with the product of the group elements. And if these are not ordinary symmetries, if these are higher form symmetries with p bigger than 0, then they have to be abelian. And that just follows from the topological structure. It follows from the fact that when I have these higher codimension surfaces associated with the symmetries, I can just rearrange them and move them past each other within spacetime, and so they have to commute. And so these higher symmetries in some sense are simpler than the ones that we're most used to because they can't be general non-abelian groups, they have to be abelian. Okay, so this notion of generalized global symmetries, as I said, it's relatively new. The paper defining them came out in 2014, even though a lot of these ideas are older. It's nice to have this new language. And in particular, one thing you learn from this language is in free Maxwell theory, if I just have a theory of a photon, I have, in fact, two different global symmetries, generalized global symmetries. One is associated with the fact that df equals 0, the Bianchi identity, which holds as long as I don't have magnetically charged objects. And that gives rise to a one-form symmetry, which is coming from this two-form current associated with the two-form field strength F. And then I have another conservation law that's just Maxwell's equations with 0 on the right-hand side. So if I have no electrically charged objects, d star F is 0, and that gives me a global d minus 3 form symmetry. And in 4 dimensions, these are both one-form symmetries. So I have a one-form symmetry, which is a product of two different U1s, one associated with magnetic fluxes and one associated with electric fluxes. The objects that are charged under this first symmetry, whose current is star F, are just Wilson loops. And the objects that are charged under the second symmetry, whose current is F, are just de Hooft loops. Okay, so basically these symmetries are just counting the line operators that are associated with electric or magnetic charges. And the interesting thing is that this simple theory that we all know very well, the theory of a free photon, has a lot of complicated structure at the level of its global symmetries that becomes apparent in this language, even if you might not have thought of it as having symmetries in just the ordinary case. Now, those conservation laws that I showed you had 0 on the right-hand side, and that's broken as soon as we introduce charged objects, either electrically charged or magnetically charged. And so these symmetries are explicitly broken. The symmetry generated by star F is broken when we have an electric current because star F is no longer a closed form. D of it is something non-zero, it's J, the current. And in this case, the operators that we were working with, these things where I would integrate the current, which is star F in this case, for the electric one-form symmetry, over some surface, these are still well-defined operators. But what changes when the symmetry is broken is these operators are no longer topological. Okay, so it's no longer true that I can take the surface and distort it and have the operator's correlation functions be unchanged. And one way to see that is a Wilson line operator can now end on a local operator that creates a charged particle like an electron. And if I link the surface with the Wilson line, I can just kind of slide that off the end, and now it's no longer surrounding any sort of charge, and so the charge is broken. Okay, so the endability of these operators is related to explicit breaking of some associated higher form symmetry. Now, this is interesting in the context of thinking about the statement that there are no global symmetries in theories of gravity, because it means that if I tell you I have a gravitational theory and it contains a massless spin 1 particle that looks like a photon, then it's not possible, if we believe that gravitational theories really don't have global symmetries, it's not possible for there to be no charged objects, because if there were, we would have these extra symmetries, these extra one-form symmetries. And as soon as we introduce electrically and magnetically charged objects, those symmetries are broken. And so we're now consistent with the principle that gravitational theories have no global symmetries. Okay, so there's content in these symmetries in the context of these ideas about what kinds of quantum gravity theories are allowed.
I'm in a meeting.
So this only tells us that some sort of charged objects have to exist. It doesn't tell us more about the objects. But if you go further and ask not just that the symmetries don't exist in quantum gravity, but that they're somehow badly broken at the quantum gravity scale. So if we go to the Planck scale or the string scale or whatever scale gravity is becoming strongly coupled at, we might expect that there should not even be any notion of approximate symmetry at that scale. Approximate symmetries kind of only emerge in the infrared. And if you take that point of view, you can actually argue that in order to badly break these one-form symmetries, you need not just a single charged particle. The electron doesn't badly break the symmetry. And the reason is that the electron gives a very mild effect on these correlation functions. So they're not topological, but if I take my surface and I change it, the correlation functions change very slowly because of the slow logarithmic running of the gauge coupling. And so what in a forthcoming paper, Cordova, Omori, and Rodelius are arguing is that this idea that symmetries need to be badly broken actually implies that these correlation functions have to be very far from topological in some regime. And that means effectively you need lots of different things running in loops that modify the potential away from a 1/r Coulomb law. And so you can actually derive stronger things like Tower formulations of the weak gravity conjecture by saying not just that we want our symmetries to be broken, but that we want them to be broken badly. Okay, so that's an interesting paper. I'm not involved in it, but I wanted to briefly mention it.
Can I ask actually one very brief question related to what you're saying? So obviously, the moment you minimally couple a U1 gauge theory to gravity, you already have, charged black holes, right? You don't need to, without introducing any elementary charged particles. There are solutions which are derived in Nernst solutions. So aren't those enough to, naively it would seem like automatically just minimally coupling the theory to gravity, you already don't have this global symmetry?
I don't think it's so clear because the black holes where you really trust the theory are the big black holes. And their effects on like the 2-point function of the photon are very small. Right? Okay. So we don't think big black holes make the gauge coupling run very fast. Now, I agree, when you have these sorts of towers of particles that come out of various swampland conjectures, they're kind of continuously connected with the small black holes. And so, so there's certainly some sense in which those two things are closely related. But I think the interesting phenomena here are in the regime that's neither well described by just a few light particles, nor by really big black holes. It's in this kind of murky intermediate regime near the quantum gravity scale.
Okay, interesting. So you're saying like this, I mean, I know you're not involved in this paper, but the argument is that there needs to be some tower of particles below M Planck.
Below the quantum gravity scale. Yeah.
Okay, interesting. Okay, sorry, go ahead, continue.
Okay. So that was the first part of the talk. I just wanted to sketch this idea of generalized global symmetries because they're useful. And also because the symmetry that I was talking about, symmetries generated by currents like F, are actually the simplest examples of this more general idea that I want to tell you about now that we call Chern-Weil global symmetries. And the idea is that the Chern-Weil currents are are differential forms that you get by taking wedge products of field strengths. Okay, so in an abelian theory, F is the simplest one. And we saw that dF is 0 if there are no magnetically charged objects, and you break that symmetry if you introduce magnetic monopoles. Now, the next such current you might think about is F wedge F. And if there are no magnetic monopoles, this is also a conserved current. D of F wedge F is 0. In 4 dimensions, that's sort of trivial because this is a 4 form, and D of every 4 form in 4 dimensions is 0. But if you're in higher dimensional gauge theories, this is a non-trivial statement. So D of F wedge F is 0, and that means F wedge F generates a symmetry. It's a D minus 5 form symmetry. But again, it's broken if magnetic monopoles exist. Now, non-abelian gauge theories are more interesting. In a non-abelian gauge theory, F itself is not gauge invariant. There's no symmetry associated with F. But there is a symmetry associated with the trace of F wedge F. Okay, and it's a fact about mathematics that D of the trace of F wedge F is 0. And one simple way to argue that is to see that you can not modify this trace by adding these commutator terms inside the trace, but those let you rewrite what's inside the trace. When I take D of this, it lets me do covariant derivatives of F inside the trace, and the covariant derivative dA of F is 0 because that's the Bianchi identity for the non-abelian gauge group. Okay, this fact about mathematics is very old. It goes back to work of Chern and Weil in around 1940. It predates Yang-Mills theory. You'll find this in any textbook that describes the theory of characteristic classes. So this is a well-known fact about mathematics. And it generalizes. I could take a trace of any number of F wedge Fs, and I get different conserved quantities for each one. Okay, so in any general higher dimensional gauge theory, we have a whole family of different conservation laws that are associated with these facts. And they all follow from Bianchi identities, just like dF equals 0 was the Bianchi identity in the U1 case. Okay, so we have this whole set of global symmetries that come along for the ride whenever we talk about gauge fields. And we've decided it's useful to give these things a name, and we're calling them Chern-Weil global symmetries. Because it's an interesting question, what happens to these symmetries? They're symmetries of gauge theory, but we've said that we don't believe that gravitational theories have global symmetries. On the other hand, we do believe that gravitational theories often have gauge fields in their infrared effective theory. So there's some sort of apparent contradiction here. Gauge theories have global symmetries. They're not easy to break because they follow from the Bianchi identity. And so what happens in a gravitational theory? And that's the question that we want to raise. If gauge theories have these ubiquitous symmetries, what happens to them in the context of gravity? And as I said, the story is kind of clearest above 4 dimensions. In 4 dimensions, it's a little bit marginal, but you could still say that trace F wedge F generates something called a -1 form symmetry. In particular, it would still be meaningful to say that trace F wedge F is exact. So there's a well-defined question of whether it's gauged. And the charge associated with that is instanton number. In 5 dimensions, instanton number is just a perfectly ordinary 0 form global symmetry. And so this question is even sharper. And in higher dimensions, instanton number is a higher form symmetry of the sort that Gaiotto and collaborators introduced. So what happens to these global symmetries? And to answer that question, we just started investigating these symmetries in the context of lots of theories that we know about. And it turns out that there's a lot of old physics that can be reframed in this language of Chern-Weil symmetries and how they're broken. And it seems to be a useful kind of unifying perspective on lots of phenomena that happen in field theory and string theory. So to give you one example, just within gauge theory, before I get to any gravitational theory, we could ask about the familiar SU2 gauge theory with an adjoint Higgs. So the case where you get an Hooft-Polyakov monopole by Higgsing SU2 down to U1. And as I mentioned, the D equals 4 case is a little bit degenerate, but we could have this discussion in any number of dimensions 4 or above. In the ultraviolet theory, we have a conserved 4-form current, trace F wedge F for SU2. In the IR, we've Higgs down to U1, and we have this candidate current F wedge F, but it's not conserved anymore because this theory has magnetic monopoles. They're the Hooft-Polyakov monopoles, so we can just explicitly construct them. And when we take D of F wedge F, we get a non-zero answer because DF is the monopole current, it's not 0. Okay, so we have a theory that has a global symmetry in the UV. It has a explicitly broken symmetry in the IR. And it appears that Higgsing has eliminated the symmetry that we had in the UV. But that should bother you a little bit, because what if I could gauge the symmetry in the UV? Then something bad is happening if it's no longer a symmetry in the IR. And it turns out that this puzzle is related to a well-known old fact about Hooft-Polyakov monopoles, which is that the Hooft-Polyakov monopole has a set of collective coordinates or zero modes. Some of them are the obvious ones that just take the monopole and move it around in space, the translational zero modes. But there's a less obvious collective coordinate or zero mode of the Hooft-Polyakov monopole, and this has been known since the mid-70s. This other collective coordinate comes from doing a kind of large gauge transformation, a U1 transformation that doesn't vanish at infinity. And it leads to a collective coordinate for the monopole, which takes the form of a compact boson living on the monopole world volume. So this is a scalar field, sigma, that lives on the monopole world volume. In 4 dimensions, the world volume is one-dimensional, so this is just a quantum mechanical theory of a particle on a circle, just a periodic quantum mechanical degree of freedom. If we're in more than 4 dimensions, it's still true that you have this degree of freedom, but now it's a field. It's a field theory on the world volume of the monopole. And if you're familiar with the quantum mechanics of a particle on a circle, you know the spectrum is labeled by some set of integers. And these integers, in fact, are exactly the possible integer electric charges that you can give the monopole to turn it into a Dyon. So you set this scalar moving around the circle with some momentum, and that gives the monopole electric charge. In the 4-dimensional case, it makes it a Dyon. And a similar thing is true in more than 4 dimensions. You can sort of dissolve electric charge inside the monopole by exciting the scalar degree of freedom that lives in its world volume. Okay, so this is an old fact about monopoles. What does it have to do with my story? Well, as I said, you can imagine gauging this symmetry. So if we're in more than 4 dimensions, we could add a gauge field, which is a D-4 form, which couples in the Lagrangian to this current trace F wedge F. And we could do this in 4 dimensions too, but there this gauge field C would become an axion-like field, theta. Okay, so after Higgsing, we clearly get a coupling of this gauge field to F wedge F in the Lagrange theory. Just when we match the operator trace F wedge F in the full theory to the IR theory, it's going to give us a contribution that's related to F wedge F. But the resolution to the puzzle that I raised before is that's not the only coupling that appears. We also get a coupling that's localized on the monopole world line. So this monopole current, you can think of as the set of delta functions that pin you down to the world volume of the monopole.
Matt, I'm sorry to interrupt, but just to follow that when you said that, you know, this is conserved trace F cross F, right? When you added Higgs field in the theory, it is still conserved?
It's still conserved, yeah.
Still conserved, yeah. So Higgsing by itself does not spoil this symmetry, right? I mean, adding a Higgs field.
Adding the field does not spoil it, right? So the conservation law of trace F wedge F just depends on the non-abelian Bianchi identity for F, and so adding charged matter doesn't.
But then in the ultraviolet, when you said that divergence of F cross F becomes proportional to J magnetic, you know, it's zero in ultraviolet then, right? If you say
in the ultraviolet theory, trace F wedge F is just conserved.
Right. So in this way, G magnetic is zero in this sense, right? I mean, in original.
G magnetic is an operator that I kind of only know how to construct in the infrared theory when I've Higgs.
Yeah. No. But you are saying that in the sense that it could be, but when you're going to short distances, you do not see any monopole because you are inside of it, right? The distance is smaller than the size, right?
Yeah.
So in this way. It's still consistent that in UV it is zero, right? I mean,
it is consistent.
Despite of existence of monopole.
Right. But the question that I was raising is what happens in the IR? How can the IR description be consistent with that?
Okay, but then we know that G magnetic is not well defined actually. I mean, in this sense. I mean, strictly speaking, because the notion of
But what I'm saying now is that within the infrared effective theory,
Yeah, okay.
You can find another conserved quantity, and it's this linear combination. So it's F wedge F for the U1.
So it's already, some field are already taken away, the one which, I mean, becomes massive, right? And only light fields are there.
Right, right. So I'm imagining flowing from this UV theory to some IR theory and trying to find a description within the IR theory.
So, sorry to interrupt. Yeah.
That's okay. Thanks for helping me clarify. So within the IR theory, we have a new conserved four-form, which is the sum of F wedge F for U1 with this localized degree of freedom, the derivative of the scalar sigma, which actually shifts under a gauge transformation, so this is a covariant derivative, times the delta functions that localize U on the monopole. And so that's the resolution to this puzzle. Gauging this Chern-Weil current in the UV is consistent with the IR theory because the IR theory does have a conserved current. It's just now a linear combination of this Chern-Weil current F wedge F and a localized degree of freedom. Okay, so again, all the physics that I'm telling you here was known in 1976. But from this perspective, you can sort of see a different route to how you might have found that physics by noticing that there's some puzzle, and the resolution to that puzzle requires this degree of freedom to live on the monopole. Otherwise, the theory would not be consistent anymore. And as I mentioned, in the 4D case, the gauge field that couples to this four-form would just be a compact scalar like an axion. And it's well known that the axion actually does couple to this degree of freedom on the monopole world line. In fact, that's exactly what gives rise to the Witten effect, which is the effect that when you turn on a theta angle, a magnetic monopole actually acquires some electric charge in that background. Okay, so that's the shift of the eigenstates of the quantum mechanics theory on the monopole world line, but they now have a spectrum that is distorted by theta. So it's no longer exactly integers, it's integers plus theta over 2 pi. And when you shift theta to theta plus 2 pi, you have this monodromy where the whole spectrum kind of marches along and each state becomes the next state. So all this classic physics of the physics on the monopole world volume and the Witten effect, you can see that it's all essential to make this Chern-Weil symmetry consistent so that you can gauge it and tell the story in both the UV and the IR and have them nicely connect to each other. Okay, so that's one example. Here's another example where now I am talking about something that happens in a gravitational theory. If I have a string theory with D-branes, say type 2 string theory, for instance, we can have gauge fields that live on the stack of D-branes. And I could make a non-abelian gauge theory, and it has a current trace of F wedge F that lives on the branes. And so you could ask, what happens to that current? Is it conserved, in which case we would have a global symmetry in the gravitational theory, and we think we're never supposed to find that. And it turns out that it's not a global symmetry because in this context it's gauged. There is a gauge coupling that takes the form of a Chern-Simons term on the D-brane world volume that couples trace F wedge F to a gauge field, a Ramon-Ramon gauge field that lives in the bulk. Okay, so far so good. We had a candidate global symmetry in a gravitational theory. I'm telling you it's not really a symmetry because it's gauged. But then you should worry a little bit because the gauge field doesn't only couple to this. The gauge field also couples to other things. This P-3 form gauge field also just couples to lower dimensional D-branes. And so the actual coupling that appears in the theory takes this kind of form. The gauge field couples to this linear combination of things localized on some D-branes, and it also just couples directly to the world volume of other D-branes. And so now I have two candidate currents, and I'm gauging a linear combination of them. But you should still wonder, is there a leftover global symmetry that comes from the other combination? And again, the answer is no. And the physics is known, and again, it's kind of old physics, but not as old as the last example. This is physics from the mid-90s, from Witten and Douglas and Green and Harvey and Moore and others. And what resolves this is that the other linear combination of these two things, besides the one that's gauged, is actually explicitly broken. And it's explicitly broken, it's explicitly broken because I can just take this instanton charge of trace F wedge F living on a DP brane. And it turns out these instantons have a size modulus. They're just standard Yang-Mills instantons, so they have some unknown radius. And you can shrink the instanton down to 0 size, or to the limits of your effective field theory description, where it hits the string scale, say. And that small instanton that's localized on the DP brane actually turns out to be the same object as a dp minus 4 brane. Okay, so the big instantons are built out of gauge fields. They're sort of stuck on the brane. But when you shrink them down to become stringy in size, they can actually be removed from the brane, and they're just a lower dimensional D-brane in the bulk. Okay, so again, there's no global symmetry here. There's one combination of symmetries that's broken by this effect, which lets us take one kind of charged object and turn it into another kind of charged object. And there's one combination that's conserved, but it's gauged. And so again, there's still nothing global. Let's see, I think I'm at about the half-hour mark, right?
Yes, you're around 30 minutes now. You know, we have another 15 minutes, ideally for questions as well, but yeah, feel free to.
So maybe I'll try to make a couple more brief remarks and then we can move to the discussion.
Sounds good.
Okay, so one other case where there's kind of an explicit breaking of Chern-Weil symmetries is in the case of Higgsing. If I Higgs a group down to a product group, say a GUT to the standard model, I could imagine building Chern-Weil symmetries for each of these groups, like trace F wedge F for SU3 and trace F wedge F for SU2. So in the IR theory, I might think I have multiple conserved currents. But in the UV theory, there was really only one that came from the trace of F wedge F for SU5. And so in this case, the IR theorist might sort of overcount. What it means is within the full theory, these things are actually broken. And only one linear combination is conserved, which is the one that corresponds to SU5. And so that tells you that there can actually be accidental Chern-Weil symmetries. They look like symmetries from the point of view of the infrared theory, but they're broken by some UV effects. And so to just kind of summarize, we're looking at many different examples. We're writing a paper now where we survey lots of different corners of string theory, and we look at candidate Chern-Weil symmetries. And we find that there are never real global symmetries in the gravitational theory. Everything is consistent with the statement that there are no global symmetries. It's consistent in an interesting way. In particular, these symmetries are almost always gauged. There are almost always these Chern-Simons terms where there's some gauge field that couples to our current. But at the same time, there's usually this kind of breaking effect. So usually the gauge field really couples to a linear combination of the Chern-Weil symmetry and something else. And the something else often involves some localized degrees of freedom. And so lots of stringy effects, like the fact that you can dissolve one kind of D-brane and another kind of D-brane, turn out to be kind of necessary for the consistency of the story. And so there's lots of familiar physics, lots of textbook string theory that it seems like you can understand from a different angle when you approach it from the direction of thinking about these symmetries and what happens to them. And since I'm out of time, I don't want to linger on this, but let me just say the 4D case seems very interesting to me as coming from the direction of phenomenology. Theta trace F wedge F you can think of as a compact boson gauging a -1 form symmetry. And again, the notion of -1 form global symmetry is maybe not as sharply defined as for higher forms, but the notion that it's gauged is when you have this kind of coupling, trace F wedge F actually becomes exact. And that seems very interesting. It's maybe suggestive of why we find axions so often in string theory. And I think it might even shed some light on the axion quality problem, although I don't have anything super sharp to say about that. So let me just mention it. And just leave you with this concluding slide. There is this set of symmetries. They're everywhere in gauge theory. They've been under our noses all along. The mathematics behind why they're conserved dates back to 1940. I'm not saying anything new from that direction. But I think it's a useful new language, and it maybe gives us a new perspective on lots of things. Okay, thanks.
Okay, thank you so much. That was a really nice talk. We do have a few minutes for questions, so any questions? Yes, just speak.
Oh, hey, Matt. I wondered if you could just say a few more words about the axion quality problem. You went by that in like 5 seconds.
Okay.
Yeah, sure, Graham. Thanks for bringing it up and giving me a chance to say more. Yeah, so what I want to say about the axion quality problem is just that, you know, from this point of view, it kind of seems like axions have a job to do, which is to take this candidate current trace F wedge F and turn it into something gauged in the sense that it's now the derivative of something else, of some other gauge invariant operator. And one thing you might worry about for the axion quality problem is, I have some instantons of QCD that couple to the axion, and I want it to solve the strong CP problem. But maybe I have some other gauge group, and it has its own instantons, and they also couple to the same axion. And generically, they'll have some other phase from the phases of quark mass matrices or whatever. And so these things can be misaligned, and this other contribution can shift the minimum of the potential, and then I no longer solve strong CP. What I would say from this perspective is, if I have these two different trace F wedge Fs for QCD and for this other group, those are different currents. And if I need to somehow get rid of both of them for consistency with these general ideas about how quantum gravity works, then there are only a few things that I know that can happen. One is that maybe they're both gauged. But if they're both gauged, that means there's two different axions, and then I don't worry very much, because the other axion can get a big mass from this, and it can decouple and leave me with one axion left over to solve the strong CP problem. Okay, so if my two currents are independently gauged, then that helps with the quality problem. If my two currents if there's only one gauging, if there's just one axion that talks to both of them, but there's some kind of breaking that lets me turn an instanton of one group into an instanton of the other group, then it looks kind of like what happens like in the GUT example that I mentioned, where you have different apparent currents in the IR, but they're all coming from a single group in the UV. And so there you really would have these different kind of instantons, but everything would have to somehow be unifiable into a single group. And so that would constrain your EFT. I mean, your UV completion couldn't be something totally general where these groups are totally independent. They have to be related to each other. And that might be useful for giving you some constraints on the model. So at least in the case where the different contributions you worry about come from other gauge groups, I think this perspective sort of suggests that within a gravitational theory, there will always be some extra structure that helps. Now, there are other things that can happen. For instance, I could get other contributions to the axion potential that just come directly from coupling it to a 4-form, which is the derivative of a 3-form gauge field. That's what happens in axion monodromy models. I don't have anything super clear to say about that case yet. So there's more stuff to think about, but I think at least taking the perspective that the job of the axion is to get rid of a global symmetry and make it a gauge symmetry seems like it might give us fewer possibilities for what kinds of things show up in our theories than we might have thought just as low energy effective field theorists.
Matt, I like to mention that with Shipman we considered some example where you're kind of going from unified group to smaller one. I mean, not in terms of gravity, but just what happened with theta angles. I mean, when it happened. But may I ask you about this instanton size, because in supersymmetric case, fixing the size of instanton is not supersymmetry, right? Because fixing the size breaks supersymmetry. So this kind of subtlety, which we were fighting with for a long time, about when we considered instanton and supersymmetry. And essentially what's going on then, that effectively you have some integration over sizes, and it becomes kind of independent, and then it could be that this integration is saturated by zero size. You see the side, what I'm asking about, that it's not just zero size of instant, but it is a special feature of instanton which makes it equivalent, I mean, to contribution of zero size instanton. And this Nekrasov localization program is of this type. You see what? So I think that it should be relevant to you as well, but it's a question.
Okay, thanks. That was an interesting comment. I'm not sure if I understood. Was there a sharp question you want me to answer, or you're just pointing out?
No, because when you said that it is zero size, which gives you P-4 brane, yeah, I reacted to this, right? That what I'm trying to say is that it should be some quantity which is not. No, it could be saturated by zero size instanton, but the phenomenon itself, it should be a little bit more generic in the sense that it, some stuff which is kind of integral over rho, yeah, because the notion of fixed finite rho is not supersymmetric.
I see. Yeah, okay, thanks. Yeah, so I guess what I really mean to say is just that within this context of D-branes, these two objects that appear in the brackets here are not really independently considered.
It's not in contradiction with what you said. Okay, thanks.
Thanks.
Okay, Sergey, he's not raised. Go ahead.
So just to understand better, so let's take a stack of D-branes, then we get flat space, and then we get typically just adjoint gauge theory living on the world volume of these guys, and that theory has global one-form symmetry, which is center symmetry, right? The end symmetry. So what happens to that center symmetry?
I see. Good. I guess the claim would be that there are always objects in the theory, right? So I'm not sure if I can answer the question without thinking through like a particular compactification, but the claim in general would be that there are objects in the theory that explicitly break that center symmetry. And
but we don't really need to compactify. We can just be in flat space, really just take flatten D space and just take a bunch of D3 branes. We get n equal 4 superior meals living the word volume, right?
Right. So in that context, I would say that we could just have some strings that end on the branes and stretch off to infinity on the other end, and then the endpoints of those strings have charge under the center symmetry, and they explicitly break the one form symmetry that you're talking about.
Okay.
If we were in a compactification, I would have to ask where the other end of the string goes, and so it's a little bit of a more complicated story.
Well, because the other end of the string should be another brane. It just means that your stack of D-branes is larger, right? But if I fix the number of D-branes, and I have adjoint SUN theory, and
right, but the string, because the fundamental strings exist, it's not really a pure adjoint theory. So there are things that carry a center charge.
Okay.
Could I make one comment about that? If you have a stack of D-branes, normally you would say, you know, there's an SUN gauge theory if you're thinking in the context of like holography. But if you're just in flat space, right, you have a UN gauge theory. And so there's a U1 one-form symmetry. And that corresponds to the, in the bulk, on the brane, of course, that's a global symmetry. But in the bulk gravity theory, that's a gauge symmetry, just like this, just like Matt described. And so the gauge charge is, you know, dp minus 2 brane charge. And so it's gauged in the bulk, and there's a combination that's gauged and a combination that's broken, just like this.
But I don't think that U1 gauge, because that U1 decouples from
it mixes with the center symmetry, right? Because the group UN as a Lie algebra splits as SUN cross U1, but as the Lie group, the center symmetry mixes them together. So I think, yeah.
Okay, thanks.
Yeah, I think Pratik had his hand raised earlier.
Yeah, I had a quick question about the way you were trying to motivate the axion using this. So did I understand it correctly that if you have a gauge group which has monopoles in the UV, then there is not a necessity for axions from the weak gravity point of view, from the global symmetry point of view?
If you have a gauge group that has monopoles.
So if let's say we have imagine we have a gut, but then the fact that there is a potential Chern-Weil symmetry for the photon does not bother us because that's going to be broken by the monopole. Is that, am I understanding it correctly?
Good. So what I would say is when you have non-abelian gauge fields, so that we can make trace F wedge F of the non-abelian gauge fields into a Chern-Weil current, it seems very difficult to completely break that without having some sort of gauging somewhere. And again, these are statements about looking at lots of examples within known quantum gravity theories and seeing what they do. We don't have kind of general theorems about what's possible. But in that case, it seems like we always expect something to gauge this, and that's sort of like, in the 40 case, that would be like an axion. Now, if it's a U1, then as you said, there's a simpler thing that can happen, which is that F wedge F can just be broken by the fact that DF is not 0, and monopoles can exist, and then we don't have a conserved Chern-Weil current to worry about. But often when you look at the U1s that show up in like concrete string compactifications, they do have these localized degrees of freedom on their world volume, like I was talking about. and then you again get some sort of current, which is of this form of the, where did it go? This form of the linear combination of two different things, and you might still have an axion that couples to this. But it's not a universal statement. So like if I just compactify a theory on a circle, and I get a KK monopole, so I have a U1 Kaluza Klein symmetry, and there's a monopole that carries the magnetic charge under it. That monopole does not have this kind of Dion degree of freedom on its world volume, and so there would not be the associated axion-like field in that case. Although it turns out the KK monopole in some theories can carry a different kind of electric charge, which is winding charge, and vice versa. So some of the examples get complicated when you start looking at what can happen with U1s. But I guess as a broad summary, it's fair to say the U1 story is less, seems less universal from what we know so far than the non-abelian story.
I have another quick question, if I may.
Very quickly, and then we'll move the discussion to Slack.
Okay. This extra contribution that you get localized on the monopole, is this the same thing as what you get localized on axion strings which converts, like usually people talk about converting consistent anomalies to covariant anomalies and so on? Is there the same phenomenon that's happening here?
I'm not sure if I would say it's exactly the same. It's closely related. I mean, I think these examples where you have localized degrees of freedom, there's generally a way to understand them in the language of anomaly inflow. Mm-hmm. And that axion string example was, of course, the first classic anomaly inflow argument of Callan and Harvey. But we think this one can also be phrased in a similar language. So yeah, there's something, there are common features to all of them, but I'm not sure if saying they're the same might be a little too reductive.
Thanks.
Okay, excellent. So yeah, feel free to go on Slack, keep asking more questions to both Quality and Matt. We'll recombine in 20 minutes at 10 a.m. for Sergey Dubovsky's talk and then Nima. So see you in 20 minutes.